Coulombs Law. Okay, so Coulombs Law is something that we will be using throughout the entire course, and so definitely commit it to memory. Coulombs Law states, if two charges are separated by a radial distance, then there will either be an attraction or repulsion of equal magnitude, a push or a pull of equal magnitude. All right, so let's break this down. First off, we need to be getting into the habit of looking at formulas and being able to describe what is happening to the system based off of the formula and really putting the formula into like a sentence form. So for example, if we are talking about a attraction or a repulsion, remember what I just described as, this is either a push or a pull. Now for us, pushing and pulling, this is just a force. So let's start off with that. The attraction or repulsion, that's a force. So capital F represents force, and I'm going to put a little subscript there for E, for electricity. This is the electric force. All right, so we need two charges. The two charges are going to be represented as Q1 and Q2. So if you have two charges and they're separated by a radial distance, right? So let's get some highlighters there. So two charges and they're separated by a radial distance. So that radial distance is just the separation distance between the two objects, and we will represent that as a r squared. Then there will either be a attraction or repulsion of equal magnitude, a push or a pull. Okay, so this is the base formula for Coulomb's law, except there's one tiny thing that goes in the formula, and that is a lowercase k. And that lowercase k represents Coulomb's constant. All right, so let's write that over there. Coulomb's constant. Now, Coulomb's constant is something that applies to any two charged objects. Okay, it is a lowercase k. On your equation sheet, you will see it written as either lowercase k or 1 over 4 pi. That fancy looking E is epsilon naught. Okay, we'll go over what epsilon naught means in the latter part of this unit. Right now, it doesn't really mean much to us, but it will pop up later. And this is going to be equal to 9 times 10 to the 9th, or sometimes you might see me write it as 9e9. And the units are, I have the units on my formula sheet, so I'll show you that in a little bit. Okay, so that is your very first formula. It is Coulomb's law. So let's break this equation down, because now we have to start thinking about what the equation means in terms of our mathematical models. So if we take a look here, and let's take a look at some relationships. So forces. So the force of the electric force between two objects is directly proportional to the charge itself. So what this means is if you have two charges and the charges are greater in magnitude, so it's like more charged up, that means that they'll exert a greater force on each other. Okay, and the other one is the radial distance. So the electric force is directly proportional to the inverse r squared. So what that tells us is that if our distance between the two charges gets closer together, okay, so if I were to do my arrows, right, if our r squared goes down, so if the two charges get closer together, that means our electric force, it goes up. Okay, so that should make sense, right? If we have two charged objects and they're super far apart, they're not going to really interact with each other. But if we have two charged objects and they're super close to each other, right, and we know that like charges repel and unlike charges attract, there's a bigger force of attraction, or there's a bigger force of repulsion. Good. So the very last thing I want to point out is of equal magnitude right here. This is Newton's third law. So Newton's third law says that for every force, there's an equal but opposite reaction force. Okay, and those forces occur simultaneously. So if you have two charges and one has a lot more charge than the other, that doesn't really matter, because the two charges will push and pull on each other with the same amount of force. Okay, so now let's take a look at where we can find all this on the formula sheet. If we take a look here on the right-hand side, the right-hand side is our ENM side. We can see Coulombs law as our very first formula. And on the left-hand side, we also have Newton's second law, F equals ma. So that will pop up a lot of the times because we will be doing free body diagrams and we will be writing out net force formulas. So I highlight that just so that we have that in mind. Cool. And the other one I want to show you is the front of the equation sheet. We see where we can find Coulomb's law. They have notated it as a lowercase k is equal to 1 over 4 pi epsilon naught, 9 times 10 to the 9, with the units of Newton meter squared over Coulomb squared. And just in case we need that in the future, we also have the epsilon naught, which is the vacuum permittivity. Once again, we'll go over what that means in the later units of 8.85 times 10 to the negative 12 Coulomb squared over Newton meters squared. All right. Okay, so the only other thing I want to go over is how we can create models of Coulomb's law. So let's dive into that. So for example, we are going to be doing a lot of free body diagram stuff. And so what we can do is we can figure out how to solve a problem, really, or how to look at a situation based on what we have. So let's say we have two positive charges, okay? And we can say that those two positive charges, because they are like charges, they will repel each other. So I'll draw an arrow going this way and an arrow going this way, relatively at the same size because of Newton's third law. But let's say we increase this positive charge by a magnitude of 5. So we'll make this a 5q. I'll just label this as q and q. Okay. So if this is increased by a magnitude of 5q, and this is just our regular q, remember, if we remember Coulomb's law, Q over r squared, the electric force and the charge are directly proportional. So if we increase the magnitude of one charge by a factor of 5, that will also increase the force by a factor of 5. Okay, and we can represent that with a bigger arrow. All right, so those are two like charges, and we can see how they repel. What about two unlike charges? So let's say we have a positive here, and we have a negative here. We can show that being attracted to each other. Let's shrink that down a little bit. I'll do another color. All right, so we can see that the two are attracted to each other. Okay, once again, the arrows are relatively close in magnitude. And if we separate the distance, maybe I should, let's try that again. All right, so let's have a positive charge here and a negative charge there. I just want to draw my arrows a little bit longer. All right, we have a electric force this way and electric force this way. The two arrows pointing towards each other shows us that they're attracted. But if we were to, let's say, increase the separation distance, so we put the positive all the way out there and we put the negative all the way out there, the attraction between them will decrease by a lot. All right. Now, the only other thing I want to show you, so we just talked about the relationship between force and charge and force and distance, is of course the graphical model. So if we are looking at a force versus charge graph, we can see that as so we have force here in newtons and we have charge here in coulombs. Okay, as we increase the magnitude of a charge, the force will also increase directly proportional. And the other one is the radius one. Okay, so we have F and let's do F and R. So when the two, let's do R here, meters, and F here in newtons, when the two objects are very close to each other, right? So when our radius is small, we have a really, really big force. And when the radius is super, super big or super far from each other, the two forces will be very, very small. Okay, the force of attraction or repulsion. So we get a shape that looks something like that. Okay, all right. So now that we're on the topic of graphical representation and graphical models, I just want to show you if we do have a data set of a F versus R. Okay. One way to linearize this data set is by taking a look at the formula itself. So we know that the formula is KQQ over R squared. Remember, the simplest way to linearize a data set is to make it resemble the formula as much as you can. So our y-axis, our f, according to our formula, it looks exactly the same. Okay. However, here I want you to notice that this r is not what it looks like in the formula. In the formula, not only is in the denominator, but it is also squared. So we need to make our x-axis 1 over r squared, okay, and our units being 1 over meters squared. So if we were to change our data set to be not just r, but 1 over r squared, our resulting graph would be a linear line. And the slope would be, so the slope would be k, q, q. All right. Now, if you're wondering, well, what about the slope for this graph, Mr. Lee? Once again, all you got to do is take a look at the formula, kqqq over r squared. So we have q on the x-axis and f on the y-axis. So that leaves us with, let's shrink this down a little bit. So we have q there and we have f here. So that means that the remainder, let's do blue there, the kq over r squared, that is our slope. So our slope is kq over r squared. The q, of course, being the opposite charge or the other charge. Wonderful. All right. That's it for Coulombs law. We have a base formula. We have the fundamental law of charges. And in the next video, I'm going to go over a couple of example problems. See you next time. Bye.